Okay. Looks like we have everyone here, and I'm here. Sorry for being a little bit late. I was running back to back from another meeting. So what we were going to do today is go over a model problem, another one of these model problems. And every time I kind of show it to you, I kind of expand a little bit more, go a little bit deeper. Let me check what we did last time to make sure I'm not duplicating here.
Can you export what you did last time so that the file doesn't get too big and we can still read it?
Yeah, I was going to start a new one.
Okay, cool. Thanks.
Yeah. So that was 13th. Let me get down to the bottom here. Actually, let me just share this, and then I think it probably is talk to it high level as we're going through. We want that. And we don't want that. Okay. You're able to see the board?
Yes.
Okay, so we had this repeat summary. We had the simple beam. Remember, we have this variational form where it's a theory of minimum potential energy. So we're just minimizing this. This functional is the ultimate goal. So we go through this variational thing where we plug in these delta U space. It's just an alternative space. It's essentially the same, but we have to call it something different. We say that we're gonna let this be U of W and L of W be a bilinear functional and a linear functional. We're gonna plug those in there, and it's essentially leads to this forced equilibrium equation where we have stuff based on tractions versus a body force that equal to each other. And we end up with this Kc is equal to F. So we're going to go through this. I'm going to call this a model problem. I'll start from scratch, start through the bottom where we do we start with the strong form, then we find the weak form. And then from there, we're going to apply our variational form. So we end up with this potential energy functional for the boundary value problem. And we'll show some equivalents there. And then we'll look at the Rayleigh-Ritz approach with that regard. And we'll expand a little bit on this K, what this K value is. And then I have this simple example that we'll write out from the problem, so you can kind of see what K is in a little bit more detail. So let's see how far we get on that, and then. Yeah, and then after that, it'll probably be Monday. We'll start talking about this whole idea of an element and how we're going to discretize an element and how that actually gets folded into this whole topic. We're slowly picking at it, trying to figure out how we're going to discretize this boundary value problem in a way that we solve it numerically. That's where we're headed. So we'll call this a model problem, and it's another way of saying strong form. Model problem. And it's in the strong form. So strong form is essentially a problem statement. It's our boundary value problem in our original domain with our normal boundary conditions, our kinematically admissible boundary conditions. So let's write this out. And for this particular problem, we're going to say that we have this a of x, u prime of x, and we're going to have the derivative of that, minus a body force, b of x, u of x plus c of x is equal to 0 in omega equals to 0 to L. And we're going to say that the boundary condition u of 0 is equal to 0. U prime of L is equal to 1. So we're dealing with something that is 1 long. And A is greater than 0. And B is greater than 0. Why do I have B in there? I don't know if I'm looking at this from an integration perspective with A to B. Yeah, I don't think we're going to use the B is greater than 0, but this kind of goes back to our problem where we were looking at x equals A and x equals B, but it looks like I'm going to integrate from 0 to L. But this right here is the strong form of this problem. It's the strong form. It's in our original omega domain. We have our function. We have the domain stated, and we have our boundary conditions clearly outlined. And this happens to be a second order differential equation, or ODE. And now we need to find the weak form. And to do that, we're going to choose a weight function, or choose a weight. Weight test function. Fingering my pen. So it's going to be W contained in this weird V space, where W goes between W and delta U. And we're going to multiply our strong form function by W and integrate from 0 to L, or it could be A to B, but we're going to do 0 to L. So we're going to have integral from 0 to L. And we get AU prime prime minus BU plus C W dx is equal to 0 for all W contained in our V space. And this is called a weighted integral statement. The way you tackle this is by integration by parts. So integral of 0 to L A U prime minus B U plus C W dx is equal to, oh, sorry. Scratch that. W dx minus integral of 0 to L B U W dx plus integral from 0 to L CW dx is equal to 0. When we look at this part, so that is our, these are our tractions, right? That's where that's coming from. So we're going to get a U double prime W 0 to L minus integral from 0 to L A U prime W prime dx minus integral from 0 to L P U W dx plus integral from 0 to L C W dx is equal to 0. Now we're going to plug in our boundary conditions. So we're going to say AL U prime L W of L minus A 0 U prime 0 W of 0 is equal to 0. So our boundary conditions.
Could you scroll up just a bit? Thank you.
This far?
No, just a lineup would be great. I mean, unless someone else. But it was just yeah.
Okay. Let me know when you're done because I need to scroll back up.
Yep, done. Thanks.
Okay. So we've got a U prime of L right here, right? And then over here I have a U prime of 0. So let's check what my boundary conditions were, original boundary conditions. So we said u0 is equal to 0, and u prime of L is equal to 1. Okay. So what we're going to get here is this u prime of L statement is going to go to 1, and our w of w0 is 0, where w of 0 equals 0 always. So this whole idea of using this weighted function is to force this. So we're basically saying this whole term right here goes to 0, right? So by putting this w term in, and we evaluate our boundary conditions, we always want this term to go to 0. If you have something else, for whatever reason, you've screwed up the problem. You need to go back. We're selecting our weight function always to force this to be 0. We want that to go away. Okay. And then we're going to rewrite equation. This is why I feel like it's like funny. It's like Monopoly money or something that we're playing with. I know mathematicians would be angry that I say that, but it feels like we're gaming the system, right? We're picking and choosing what we want to make that to go 0. Integral from 0 to L, a u prime w prime plus b u w dx is equal to 0 to L, integral from 0 to L, cw dx plus a at L wl. And now this gives us our weak form. Now the weak form. And you have to write out this whole thing here. Find u contained in delta such that b u comma w is equal to lw for all within this V. Delta is equal to our displacement field, which is valid in a H1 space from 0 to L, or H1 continuous, where u of 0 is equal to 0. And our V space, W, where W is H1 continuous from 0 to L, W, 0 is equal to 0. And B, u of W is equal to the integral from 0 to L, a u prime W prime plus b u W dx, and LW is equal to integral from 0 to L CW x plus a L W L. So this whole thing is our weak form problem statement. This is the boundary value problem that we need to solve using finite element method. So we haven't done anything finite element yet. We are starting with a strong form boundary value problem. So it's in its original domain, and we can, and and this particular thing happens to be a second order ODE. We can solve that. We can find an exact solution to that ODE, more than likely, by hand, right? And you folks remember from DE, that's nasty, right? I mean, an easy problem, you're talking 1 page. But imagine solving that problem for your potato. For all of these different nodal values and things. It's impossible. So we can't do that. We know we can't do that. We have to figure out another way. So wonderful mathematicians figured out this problem that we can find this weak form solution that approximates our strong form solution using this weighted function. And the weighting function is W. And yeah, the W is arbitrary because it's arbitrary. And we're going to pick that, that W to make sure that W at 0 always equals 0. So it's at the boundary condition, right? So this is the task. This is the weak form, and this is what we're here to do. And now we need to continue. So we've got our weak form. And now let's write out the variational form. Of the weak form. And so what we get is B UW, BU delta U is equal to L delta U for all delta contained in this V space. Obtained by delta variation equals to 0 for our variational displacement being the potential energy. Where B U W is equal to the integral from 0 to L. This is an AU prime, W prime plus B U W dx comma L W. We don't want to rewrite that. And B U W is equal to B W U. So if you remember all the way back from the beginning of the semester, what I'm implying here is that this is symmetric And if you remember, it's a bilinear form for this one. And our variation of u is equal to 1/2 b u comma make sure I have this consistent. Hold on, I think I found a error in my notes. Please. Yeah, so this is B delta or BU delta U. For some reason in my notes, I didn't have the delta in there. Minus LU. This is the potential energy function. So put a double star here. Now we have to verify that. So we're going to look at our delta variational is equal to 0. So this is 1/2 b u delta u. Plus 1/2 b delta u u minus L delta u is equal to 0. And because of symmetry, we can state b u comma delta u is equal to L delta u for all delta u contained in our V space. So variational form comes back. Basically, these two cancel out, right? Because we're swapping the terms, the u and delta u. That's all we're showing is that there's symmetry there. So that comes back. So writing it out all over again. 1/2 0 to L A u prime squared plus b u squared dx minus the integral from 0 to L cu dx minus a L u L. This is the potential energy functional verified for this boundary value problem. Okay. So now we look at the Rayleigh-Ritz approach. So remember, that was u of h of x is equal to the sum of I is equal to 1 to n that's a horrible phi. That's supposed to be phi. Phi j x cj for all delta, and this is considered a trial solution. Okay. Now choose your choose your phi j of 0 equals 0 for all L. And test the weak form function. Okay. So pick W of H of X to be equal to phi I of X for I is equal to 1 to n for everything contained in this V space. This W is a test function. So remember, we picked this test function to force it to be 0, like W of 0 is equal to 0, right? The problem doesn't work unless we do that. But now we're going to say that that's equal to this trial solution, this phi. Again, monopoly money. So now we're going to substitute U of H and W of H into our weak form. So we're going to get B is the sum of j is equal to 1 to n, bj x cj, comma, b of I x is equal to L phi of I of x for I is equal to 1 to n. Whoa, what happened?
Woo.
So what are you, we're seeing these index. So if you remember back from the beginning of the semester where we're looking at materials, what do these indexes tell you? There's a whole family of equations here, right? We're not talking about one equation. We're talking about a whole bunch of them, okay? So this whole thing implies this sum of j is equal to 1 to n, b Vj, comma, Vi, Cj is equal to L, Vi, and if this portion here does anyone know what this is?
Is it a gradient?
The sum? No. Those of you that have done finite element stuff will know when I write it. It's the sum of K, Ij. It's K matrix. Cj is equal to Fi, or I is equal to 1, 2 to n. And this is symmetric because B is symmetric. Remember we said that before? The BU, delta U, and BUW, all those are symmetric. So K, I'm going to say underscore because it's a, we can write it as underscore, or we could write it like this as a matrix, write it as an underscore K underscore C underscore is equal to F underscore, and then solve for C to get solution. So remember what we're doing. We have a mechanical problem. We're applying loads, right? So we know what F is. We know what the forces are. That's a known. K, we're making some assumptions that we know what that is. It is a J equal to B, Vi, comma, oops, Vj, Vj. So this Kij is equal to this, but where did B, let's remind ourselves, where did B come from? Where did this whole B thing come from? Let's go all the way back. Go all the way back. So
Is
We-
it the bilinear functional?
it's the bilinear functional, but let's go all the way back to our problem statement. There's no big B in here. We have this force equilibrium type equation. We know this AX times U prime of X. We know that this is our tractions, right? Tractions and body forces. And we go through this process. So we need to find the weak form. And part of that weak form is we're basically just changing the domain that we have that in it. So we're adding in this, this weight function. and we're integrating. And what comes out of that is we're allowed to set this part of the equation here to 0. This is basically our fixed boundary condition. Is this A0, U prime 0, W0, right? That's the fixed end of our component. It's the tractions where we're saying everything, there's no displacements. Displacement fields are 0. So we don't care about that. Everything's 0. We're ignoring that. We don't care about anything that's going on there. We want to know what's going on at the other end. So we have this, we're kind of whittling away at this. We have this weight function in it. We've now taken our derivatives and we've integrated it. And we find this weak form of the solution. And we're basically saying this weak form of the solution, we're breaking it up into 2 parts. And we're saying this part right here, the AU prime, W prime plus BU, this is the first part, AU prime, W prime. That's a weighted, it's the tractions, right? That's our area times our stress, if you will, and it has a weighting function on it. Plus our boundary, our body forces, right? That's what that is right there. And we're calling this BU of W, right? So this BU of W is very loaded. It's this huge statement right here that's going on. And then we take the variational form of that. So we're saying, okay, well, we have this weak form solution that has this weighting function in it, and it's in a different space. Well, now we're going to take the variational of that. And we know that this B function is symmetric. It's a bilinear form. And we're going to apply this theorem of minimum potential energy, or the potential energy function. So we're going to simplify our problem, keep plugging away at it, and we end up with this potential energy. So it's essentially it's a spring, right? That's what we're talking about that we have right now. We have a spring. It has potential energy in it, and now it's like, okay, how we break this up? How do we solve it? So this Rayleigh-Ritz approach is, okay, we need a trial solution. Let's make something up. We're going to say that this phi is basically, this phi of x Cj is our trial solution, and we're going to pick that at our boundary condition, this phi of 0 is equal to 0. And now we're going to pick another test function that we're going to plug into this Rayleigh-Ritz method. We're going to substitute that into our weak form bilinear functional and our linear functional, and kind of sort through this, and it gives us a little bit different form. Now, what you're seeing is we're getting this into index form, right? So I think the way I want you guys thinking about this right now is it's a very I don't want to say archaic, it's a very complex way of taking this second order ODE that we don't want to solve by hand, and it's now in a matrix form, right? I mean, we don't know what the matrix really looks like or what the things are in there. I mean, we'll explain that in a second, but we're in a matrix form now. Doesn't that make it way easier to solve once you're in a matrix? I mean, we can find the eigenvalues, we can find the eigenvectors, because we're in a matrix form right now, and we've simplified it to basically, I mean, this is force is equal to, almost stress times strain type. Doesn't this look like Hooke's law? We have this bilinear functional is equal to this C matrix that's equal to our forcing matrix. And if we look at our indices, what is F? F is a column vector. C in this particular case is a column vector, could be a row vector, but we don't have a transpose on it. And K is our big one, right? This is our big one. So from a finite element perspective, K is our stiffness matrix. This is where we're getting our stiffness matrix from. This is the thing that we ultimately need to get at. So if you can see this, we have this K KC is equal to F, and I'm saying, okay, we need to solve for C to get the solution. How do you solve for C? These are matrices. So can we state this? So so we have K. C is equal to F. So this is you know, a matrix, a vector, and a vector. Do you guys remember your matrix stuff? Can we just solve for C? Can we just say that, you know, C is equal to F over K?
You have to use K inverse on both
Yeah,
sides.
it doesn't work that way, right? This is like a way no go. We actually have to multiply by K inverse, right? But do you remember what that process is to invert a matrix?
Yeah.
Like,
So
if you were to do it by hand, it sucks, right?
It's a nightmare.
Now think about doing this over and over and over and over and over, you know, millions of times. Like computationally, it would take forever, right? Because you're having to invert this matrix. You're having to take the invert of it so you can solve for C. This is the crux of the finite element program. This is the crux of why the freaking solutions take forever to get. This is what the program's trying to do, is solve for C. But in order to do it, it has to invert this K matrix to solve for it. And can you see that, you know, this K matrix, the way we have it right here, I and J, I haven't specified that this is I is equal to 1 to 3. It's 1 to n. This matrix could be massive, right? And to try to invert that and do your multiplication from a processing power, that's horrible. That's horrible. So that is the crux of why the finite element solution takes forever to solve, is because of exactly that problem right there. You have to solve for C, and to do it, you've got to invert K. Okay. So to give you an example, this and maybe this isn't obvious. Maybe I didn't point this out. Do you guys see that this L phi of x is F?
yeah.
So okay. I just wanted to make sure that I didn't gloss over that. So maybe we should write that out. So the so here we have our K ij is equal to this to that, but our our Fi is equal to, well, I guess to put it in the same form here, is equal to L B I. So we know this. We think we know this. We have to calculate it. But these B's, these bilinear things are nasty, right? So if we want to look at kind of what this looks like expanded a little bit, so kind of a sub example. Model problem. I haven't heard any ahas over this. I was kind of expecting some ahas over this whole thing from you guys. Is it just too late?
Ahas over which part?
That this is what where the K matrix is coming from, where it's really coming from, and that it's like, oh my gosh, that is a big matrix. It is going to take a long time to solve. So we have phi x is equal to x, and so I'm choosing this phi I of x is equal to x, and this phi 2, actually it's not I, phi 1, 2 of x is equal to x squared. I'm just making something up here because I want to show you what this K matrix can look like to hopefully give you the aha moment. And our U of H of x is equal to phi 1 x C1 plus phi 2 x C2 for all delta. And in that particular case, our K matrix would look like B phi 1 comma phi 1 B phi 1 comma phi 2 and B phi 2 comma phi 1, and this is symmetric. So you see we go through our indices 1, 1, 1, 1, 2, and then down here it's symmetric. So this would be a 1, 2, and a 2, 1.
Does this be a phi 2 on the bottom right?
Yes, phi 2, phi 2. Thank you. And if we wanted to expand that for what those look like in more detail, we can call this, I'll just call it A underscore, so you're not stuck with one form. But what this bilinear functional looks like is actually the integral from 0 to L A phi 1 prime squared plus B phi 1 squared dx. And then our second term is a phi 0 to L A phi 1 prime phi 2 squared plus da, da, da. So the point of this is that these are integrals. These are these huge integrations that have to be done as the individual terms in this matrix. And synonymously, the F is the same thing. They're, the integral from 0 to L C phi 1 plus A L phi 1 L. So it's not like this is an easy task to get this, right? To get these individual terms, you first have to figure out a way to do the integration routine, which we know that you can't do an exact integration numerically. So we have to have some numerical scheme to do that. And then once we get the values populated in this K matrix, we have to invert the thing and do our multiplication by it. So it's a very, very computationally expensive routine to solve. And remember, this is all based on a displacement, right? This is all based on a displacement field. And so is the displacement field constant? It's not. Our displacement at every integration point is different. And the reason I say integration point is these are integrals. And right now we haven't defined where those locations are. That's what's missing in this, right? I haven't talked about this potato. I haven't talked about, okay, we have this KC is equal to F, and it's in some delta domain. But I haven't said where, right? So let's say that I'm doing that here. I'll kind of let you guys believe that we're doing this at a node. We're not doing this at a node long term, but let's say we're calculating the displacement here at this node. That displacement feeds into a particular K matrix for that displacement field. Whatever is going on at that displacement field, which means I have a different K matrix here, and I have a different K matrix here, and a different one here, or wherever you're doing this. And let's say that you're getting fancy and you're not going to integrate, you're not going to actually do your integration at your nodes. Maybe you're going to do your integration, this is more reality, somewhere within the body of this little element. And okay, now we're doing this calculation at each one of these points. And we get a solution for each one of those values. Do you remember? So this is done at a you're calculating all of this at a local coordinate system. We still have to map back to our global coordinate system. So just because we have a solution here and we've done this K matrix inversion and we say, yeah, we're a cool guy now, we figured out what C is, at that point, we still have to do the math to map it back to our global coordinate system. So there's a lot of steps in this that it's very, very time consuming. And I think we take for granted what's going on behind the scenes when we're doing this FE approach. So anyway, I feel like I'm more excited about this than you guys. I'm disappointed. Okay, so I think that's probably a good stopping point for tonight, because what we'll do on Monday is we'll basically start from the top again. We'll start from a strong form, and I'll go strong form directly to the weak form. We'll skip all the steps in between because we don't really care about that. We'll outline a much quicker process for our minimum potential energy and all that. And I'll give you some general rules for some of the things some attributes that the K matrix has to possess. Like for instance, it has to be a full matrix. It can't be sparse. So if you get a solution and you have missing elements for whatever reason in your stiffness matrix, if you're programmatically doing this, you would have to throw an error code that there's something wrong in the mathematics, and the solution's bogus. So you'd have to ditch that. And then we're going to get into this idea of trying to link this stuff, our bilinear functional, to this finite element idea in a one-dimensional array. And that's where we talk about our Lagrange polynomials. And this is where we do our mapping. This is where we do our mapping to figure out what our element formulation is. And essentially our element formulation is going to be another, almost like a weighting function that's plugged into our bilinear functional. So it's changing our space again. We're going to go from this coordinate system that we're in now in our subdomain in this omega domain, and we're going to go to this Z space, C space, where everything has to be related to 0 and 1, and not, integrating from A to L. And we have to figure out the math and the geometry between what I laid out here, between all of these integration points. And we're basically defining the mathematics for how this element is going to work. And this is essentially the mapping, how we're taking our boundary value problem in our KC equals F, and we're applying it specifically to this meshed body. And where we're taking those integration. And that's where we get our elements, our nodes, these things called integration points, and how all of that sorts out. So there's a whole little sidebar on figuring out this isoparametric mapping and how that relates to our problem and our bilinear functional. Okay. Sound good? So I apologize for being a few minutes late tonight. I hope you all have a great weekend.